Okay, so today we are going to start a new chapter, which is about polymer. Yeah? So polymer is among the 4 types of basic material structure, which are metals, ceramics, polymer, and later next week, hopefully we can discuss on composites. So about polymer, so there will be 2 main discussion about polymer. The first is about its structure, and number 2 is about its processing and also application. So what the issues to address in this first part, which is about its structure, is what are the basic raw structural features of polymer? How are the polymer properties affected by their molecular weight, by the molecular weight? And then how do polymeric crystals accommodate the polymeric change? So what is basically a polymer? What is a polymer? So in contrast with the previous 2 types of material, yeah, in metals we have mostly the large elements, yeah, the heavy elements like iron. Well, there are some light elements like lithium or sodium, which are also considered as metal. But in our daily life, mostly we perceive metals as those which are heavy and strong. Then there is ceramics, which is also made from various compound, made from different kind of elements. Yeah, many of them are also heavy elements, but with the addition of sometimes oxygen also. In polymers, mostly they consist of 2 main uh, elements, yeah, which that are the carbon and the hydrogen. The carbon and the hydrogen. These carbon and hydrogen atoms form the backbone of many polymers. And then there might be some additions to the branches, sometimes also at the main backbone from oxygen, sulfur, nitrogen, and in several cases also with metals, which we call as metalloprotein, metalloprotein in the case of protein. So polymer, as the name implies, consists of 2 different original words. The first is the word poly, which means many, and then the word mer, or repeating unit. Yeah. Let's see some examples. Polyethylene, yeah, Pe, which is used to make, for example, a plastic bottle. This consists of only actually carbon and hydrogen. Yeah, carbon and hydrogen, CH, and the basic mer here is the C2H6, basically, C2H6. Or when you cut the ends, it becomes only C2H4 or ethene, ethane. So when this ethene is, or ethylene, yeah, is being repeated, it binds to other 2 ethylene, then they will make a long chain of polyethylene, yeah, repeating ethylene basically. Another example here is polyphenol chloride. This has an additional atom called chlorine, chlorine atom, additional chlorine atom from the group 7, in the periodic table, which is very electronegative. The chlorine may replace one of the hydrogen atom in the normal ethylene and makes what we call as ethyl chloride. And when this ethyl chloride binds to other ethyl chlorides on both ends, it will also create a long chain of polyphenol chloride, PVC. And this is used for fabricating mostly piping, pipe, PVC pipe, we call it, about PVC pipe and other strong plastic. Then polypropylene or PP, polypropylene, made from the basic mer, the basic repeating unit, propane. Propane. Propane has three carbon atom in its backbone, C triple C. Then, however, in the second carbon, it branches. One of the hydrogen is then replaced by another propane, another propane. So to form this long chain of polypropylene. So in the past, even before polymers now are widespread in our daily life, it's used basically everywhere, from house appliances, bucket, sometimes also plates, spoon, packaging, etc. But in the past, they are not like that. Yeah. So in the modern polymer, mostly they are synthesized from oil. In the past, mostly people use only natural polymers, which, for example, are the wood, from the forest, cotton, which is usually cultivated from cotton trees, taken from the flower part, leather from animals, rubber also from rubber tree, wool from this is from animal, and silk from cocoon. All these non-uses of these polymers are, for example, rubber balls used by Incas to play the soccer in the ancient time. Then Noah, one of the prophet, he used pitch, a natural polymer for the ark. So polymer composition, they are mostly made up of hydrogen and carbon atom. That's why they are called as hydrocarbon, atoms. And in saturated hydrocarbon, as maybe you have learned from chemistry 2, or chemistry 3, in the third or second semester, each carbon is bonded to four other atoms. Remember this kind of molecular structure? So when it is drawn like this with a solid sharp triangle, it means that the structure is protruding towards us. And it is built with dash line here, it means the structure H here is going towards the screen. So this is an ethane molecular structure C2H6, saturated, which is a kind of saturated hydrocarbon, because each of the carbon, covalent, each of the valent electron in the valence shell of the carbon is bonded to one hydrogen or to another carbon atom. So the formula is Cn, H2n plus 2. And the composition are like this. Yeah? So we have methane for alkane structure, composition molecular structure for some of the paraffin compounds, CnH2n plus 2, methane CH4, like this, ethane C2H6, consisting of two carbon atoms that make the backbone, propane C3H8, butane, pentane, and hexane. As we see from here, as maybe I think you have learned also in organic chemistry, that the more atom you have, right, the more carbon creating the link, creating this long chain that you have, and which means also more hydrogen atom. It means there are more bonding there are more bonding exists there. So when we boil this kind of structure, when we boil this kind of molecule, it needs more energy to dismantle every single bonding. That is why when the number of the atom in single molecule is not that many, like in methane, the boiling point will be very low, minus 164 degrees Celsius. It means it is already in gaseous state in room temperature. With ethane, also similar, we have also gaseous state in room temperature, but it has a higher boiling point compared to ethane. The ethane's boiling point is minus 88.6 degrees Celsius. Propane will have also further higher boiling point temperature at minus 42.1 degrees Celsius. Butane has further higher degree at minus 0.5 degrees Celsius. So uh, these four alkane chemicals are therefore a gaseous state within room temperature. Yeah. So when you need to transport them, you usually have to compress them. That's what we have in our LPG, and also compress and even make them into liquid state. LPG is liquefied petroleum gas. Yeah, basically from petroleum we have these four light gases: methane, ethane, propane, butane, and we have also LNG, liquefied natural gas. When the molecular structure grows bigger, with like in pentane and hexane, then as can be expected, the boiling point will also increase. So pentane has 36.1 degrees Celsius, hexane 69 degrees Celsius. Therefore, you will see these two molecules as liquid state in the room temperature. So sometimes not all of the vacancy of electron that carbon atom has will be allocated for hydrogen atom. Some of them will be used to bind to the same carbon atom. So in this case, then you will have unsaturated hydrocarbons, double and triple bonds between the two carbon atoms, and they are usually relatively reactive. It means they can be easily released to make a new bond with whatever a new atom that comes, as long as it fits with valence to make a covalent bonding. So for example, here we have double bond in ethylene or ethene with the formula of CnH2n. Yeah, like this, the two double bond between the two carbon atoms. So you have 4 bonds, but only 3 atoms bound to the carbon covalent. Yeah, 1, 2, 3. Then we have triple bond molecules, where, for example, in acetylene or ethine, with the formula of CnH2n minus 2. Between the two carbon, the main two carbon atoms, there are they form 3 bonding. So they only bind to one single hydrogen atom, each of them. In organic chemistry also we have learned about isomerism. This is where when two compounds with same chemical formula can have quite different structure. This is usually fine. This usually can be found when we have very large molecule with large main chain. Yeah. For example, in octane, N-octane, N-octane, CH, the 18, formula is like this, but it can have various different structure. It can be like just one single long chain, where we call it as N-octane, consisting of 8 carbon atom connected in one single chain, and each of the carbon binds to 2 hydrogen atom except the 2 atom at the 2 ends. Then we can also have, so this is if we rewrite the formula, rewrite the structure in contracted way, abbreviated way, we can abbreviate, or we can shorten the middle structure as CH2 repeated 6 times, connected to CH3 at its 2 ends. This CH18, the octane, can also have this kind of structure where it has branches. First at the second carbon atom, as well as at the 4th carbon atom. So we call it as 2-methyl because here at the second carbon atom, it is connected to 1-methyl functional group, and 2-methyl for ethyl because it is connected to ethyl functional group at its 4th carbon atom. pentane. Why it is called pentane now? Because the main chain only consists of 5 carbon atoms. So 2-methyl 4-ethyl pentane, or the other name called also as isooctane. So these are polymers. So there are some naming convention by Iupac, International Union for Pure and Applied Chemistry, on how to name such structure. So in organic chemistry, it is very important to also know the molecular structure of one single compound, because even though they have the same name, the same chemical formula, they might have different chemical structure. So how actually are polymers made? So these are made through several steps of chemical reaction. The first one is through the what we call as free radical polymerization. When a free radical, this free radical can be something which will bind easily, or which will create binding easily to the to the monomer that we want to make as polymer. So this free radical can be introduced in the industry. It can be introduced by the manufacturer to initiate polymerization. So the free radical, for example, here will bind to ethylene, which acts as a monomer. R here with a single dangling bond. Dangling bond, it means, like, for example, a single electron that doesn't have yet pair, so it seeks for pairing with any valence electron in the carbon atom at the monomer. So since this monomer has double bond, which means that it is unsaturated, and as we have learned, it can release it easily, because the energy is not that high, can be released easily to make a more stable binding with this free radical. So it will form RCC, RCC 4H for hydrogen atom. The first carbon has find its binding, its new, has formed a new covalent bonding with the R. However, the second carbon is left without anything to bind to, which makes the whole thing becomes a new radical. Because it now, this carbon has a dangling bond. Dangling bond is again is an electron which is actually seeking for a pair to make a covalent bonding. So this process is called as the initiation. Since this now becomes a radical, it can then react with another ethylene molecule, another monomer, to also dismantle one of its double bond, to make a longer chain of molecule, which then it becomes dimer for monomer, one mer, to become dimer, two mer. Okay. The same thing happens also with this dimer, because the carbon atom at its end, one of its ends, does not have yet any pair of atom to bind with to make a covalent bonding. This will become then a radical. So this radical, along with maybe other new radicals, will try to bind to the monomer, which is not yet reacting, not yet reacted, make new radical, and then this expands. This radicalization expands throughout the whole molecules within that sample, within that particular case. So the process of this, what we call it, reactions, where the radicals makes new radicals, make new long radicals, etc., is what we call as propagation. The main chain of that polymer will be extended as soon as it binds to a new polymer. So theoretically, when this propagation is not stopped, it can bind to very long monomer to make a very long chain of polymer. This is and you may ask, what is then the example of this radical, free radical? So this is the example. It can be made from benzoyl peroxide. Benzoyl peroxide has this structure, yeah, consisting of phenyl. This is a phenyl functional group, yeah, connected to this CO carbonyl functional group, double, yeah, double benzoyl peroxide. And when we cut this benzoyl peroxide at the middle between the two oxygen atom, it will mix to free radical, because now the oxygen atom has one electron, also one dangling bond, which is ready to seek for a monomer to bind with and to make initiation. And then further later it becomes propagation. Okay, so from one benzoyl peroxide, two free radical can be made. So this is the this is ethylene, polyethylene. This is the repeating unit, shown like this one. Yeah, so it is not, in reality, it is not two-dimensional structure like this. Yeah, in reality, it actually has this three-dimensional, because the binding between C and C has certain angle also, not just single straight line like this one. This is this structure depiction is just to make it easier to write on paper, but in reality, it will be like this. Yeah, the carbon form a tetrahedral structure with four other atoms, two carbon atoms and two hydrogen atoms. Polyethylene is an example of a long hydrocarbon, while paraffin is a short version of polyethylene. Okay. So let's give some example of bulk or commodity polymers that are widely available, or we can see them easily in our daily life. So polyethylene, as we have mentioned many times, polyphenol chloride, we have also mentioned this is material for plastic pipe, plastic tubing. Ptfe Polytetrafluoroethylene, this is used for some hard packaging. Yeah, some hard packaging. It contains fluor. Yeah, the four carbon hydrogen atoms are replaced by four fluorine atom, becomes polytetra. So that's why it is called as tetra. Tetra in Greek means four. Polytetrafluoro. So four fluoroatoms, fluorine atoms, ethylene. So the basic structure itself came from ethylene compound. Then we have polypropylene. Yeah, polypropylene, basically it comes from propane. Yeah, only then it makes binding at its second or the middle carbon atom. So it looks like, also you can say, looks like ethylene. Only one of the hydrogen atom is replaced with a single methyl functional group. Polystyrene. This is also similar in its backbone, like polyethylene. Only one of the hydrogen atom, is replaced by a phenyl functional group like this, yeah, benzene cyclic group. Polymethyl methacrylate, yeah, PMMA, or in the market we usually call it as acrylic, and it is used for making aquarium or many other structure. So this one of the hydrogen atom is replaced by methyl functional group, and the other is replaced by this COO carboxylate with a single methyl group as well, carboxylate functional group. Phenol formaldehyde or bakelite. This originates from a single phenyl functional group, which binds to methyl, another methyl, three methyls, yeah. Three methyls on its three outer ring structure plus one single hydroxyl functional group. Then nylon, yeah, material of clothing is made. chemical name is polyhexamide methylene adipamide. And this has more complex structure. The repeating, it has a 6 repeating structure of the CH and 4 another 4, and between the two, it is connected with an with NH group, and as well as CO carboxyl group, carboxyl functional group. Amin, yeah, amin. Then PET, polyester, also a material for textile, or polyethylene terephthalate. In its chain, it has this phenyl connected to carboxylate functional group, which is then connected to ethylene structure. Then polycarbonate, PC, this is also has 2 phenyl functional group on its backbone. Okay, so it can grow that long, and we have seen that it may eventually stop when we absorb the radical, so that then it doesn't react anymore. So in polymer, then the molecular weight will be dependent upon the length of their chain. Okay, so that's why Mi molecular weight of polymer is the mass of a mole of the chains. When the chain is short, then you will have a lower lower molecular weight compared to if we have very long molecular chains, with higher molecular weight. In one single polymer, it may contain multiple different chains with different length. So it's not always that one single polymer, let's say suspension or whatever, has only a single length of molecular chains. It may vary. And this variation of molecular chain is then graphed as this kind of distribution. Then the average molecular weight will be calculated from this total weight of that polymer divided by the total number of the molecule. So this molecular Mn, molecular weight can be calculated also sigma xi multiplied by Mi. What is the number? Xi represent the number of the molecule inside the polymer that has Mi molecular weight, or Mw sigma Wi times Mi. So Mn here is the number average based on the number of the molecule that has certain length of chain, while Mw is the weight average, calculated from the weight of each of the molecular weight. Mw average is more sensitive to higher molecular weight. This can be seen from this distribution. So the y-axis here indicates the amount of polymer that has particular molecular weight within that ensemble of material. Okay, so as we can see, let's say for example this is polyethylene, then the number average will be here. Then the number of longer chain of polyethylene is smaller and smaller and smaller. Similarly, below that number average. This is the weight, molecular weight distribution. The calculation of average mass of a class is, this is for example, to understand better the molecular weight calculation. So for example, the number, how many of the students that has 100 pounds of mass. For example, we have 1. How many number of students that has 220 is 2. So we list this the number of students that has particular mass. And xi here is the fraction from all the number of students. So the total of this student is 1 plus 1, 2 plus 2, 4 plus 3, 7, plus 2, 9, plus 1, 10. So the number of student, the fraction of student that has 100 pound of mass is 0.1. The fraction of student that has 120 pound of mass is also 0.1, etc., etc. The weight fraction is indicated by this one. So what is the total weight, total mass of the whole thing? Yeah, from here 100 plus 120, and then this weight fraction is this 100 divided by the total weight. Okay, so from here then we will obtain the Mn average mass is 0.1 times 100, yeah, plus 0.1 times 120, etc., etc., and then we'll obtain 186 pound. If we calculate using the fraction weight, yeah, then 0.054 multiplied to 100 plus 0.065 plus 120, all the way until the 0.204 times 380, and then we will end up having 216 pound. Okay, so that is why usually weight average is more towards the higher molecular weights. The degree of polymerization, or N, is the number of repeating units per chain. Okay, so for example, if we have this polymer, and we know that polyethylene, yeah, this is again polyethylene, one single monomer consists of this one ethylene mer, and how many times is this monomer repeated along this chain? So 1, 2, 3, 4, 5, 6. So we have 6 times of polymerization, degree of polymerization. So the N is calculated. Again, this is similar like the calculation of molecular weight. Now the degree of polymerization is the sigma of the fraction of that particular degree of polymerization within that sample, and then the sum of it. And then basically this is equals to the what do you call it, number average, the number average of the mass divided by the average molecular weight of the repeating unit. Yeah, average molecular weight of the repeating unit here. The M here can be calculated from sigma Fi, the chain fraction, multiplied to Mi, molecular weight of the repeating unit I. If we calculate the degree of polymerization based on weight average, it's like this: from sigma of the weight fraction of particular molecule of polymer that has n I and I degrees of polymerization. This is equals to weight molecular average MW divided by average molecular weight of the repeating unit. Yeah, this is calculated by sigma of Fi, the chain fraction, times the Mi, the molecular weight of that repeating unit I. So the structure after this what we call as the primary structure. Yeah? When we have repeating unit, polymer, one single chain, depending on short, it can be short or it can be long. This is the primary structure. What, how many times the monomer is repeated, etc., etc. But when it becomes very long, then it may create a secondary structure. It may create this kind of spiraling structure. Yeah, sometimes spiral, sometimes helical structure, etc. And then further, it will create tertiary structure. Tertiary structures, for example, here, it creates this kind of maybe a scissor-like structure. And the distance r here is to indicate a parameter that indicates the distance between one end of that polymer to the other end. Okay, end-to-end distance r. The molecular structures also of polymer can be various. It can be linear, as mentioned earlier, linear between polyethylene, we have linear. But then between the two different chain, there might be a secondary bonding. Could be due to the hydrogen bonding, could be due to van der Waals bonding, or other electrostatic bonding. It might be branching. Yeah, the chain does not only, for example, one single chain, but it may branch in on some of the molecule, making another shorter chain. Or then the structure may become cross-linked. This is when one chain of polymer is bonded to another chain of polymer through a monomer also. Yeah, like this. Of course, the structure then will have a stronger structure compared to the other two here. Another strong structure is when between the monomer, it creates a network structure like this. So not instead of a single long chain, it becomes like this web-like structure. So as you see here, from left to right, the strength increases because of the more complex structure, because the structure is more untangling from between one chain to another. Then conformation is the molecular orientation can be changed by rotation around the bonds, although we don't need to break the bond. Okay. So for example, here this can rotate, this one can rotate, this one can rotate. So make, for example, a different structure like this. To change the structure, a polymer must break the bonds and remake the bond. This is, for example, in organic chemistry, we know there is a phenomenon called as stereoisomerism. They have the same, exactly the same structure, only, for example, in one molecule, the R is located here in the down right. The other one is located at upper right. So mirroring to each other. For example, here, the chemical structure is the same, A, B, C, D, E, like this, but they are located at different place. When we have mirror like this, so this is called as stereoisomerism. So the different structure is not due to the branching of the chain, but rather because of the one of the functional group is located at different location of the molecule. Tacticity is the stereoregularity of chain. So in isotactic, all the R groups, functional group, are located on the same side of the chain. When you have the R groups in alternate sides, for example, is R, and second after that is on the upper part, then again lower part and upper part, this is called a symbiotic tacticity. Atactic is if the locations are completely random. It's sometimes down in the lower part, the other sometimes in the upper part. So this is a atactic. Then we have also in polymer what we call as cis-trans isomerism. In cis, for example, in natural rubber. So basically, this is a kind of stereoisomerism. So they have similar structure, right? Here one methyl functional group and one methyl which is binding to another. This is another one binding, but here this is located in the upper part. Okay, so the bulky groups, which is the binding, which binds to the other monomer, is located on the same side of the chain here on the lower part. In trans configuration, like in trans isoprene, the bulky group located on opposite chain, opposite sides of the chain. Can also have copolymers. This is where two or more monomers are polymerized together. Like this, the black represent the B, the red represent the A. It could have random copolymerization. A and B varies randomly within the chain. could be alternating. So A and B alternate in this polymeric chain, or could be as large blocks of A and alternating with large block of B. Otherwise, they make copolymers as graph. Chain of B here grafted onto the A backbone. Okay, this is different ways of copolymerization. And yeah, maybe we are not, this is a bit, we are, we take it a bit difficult to perceive, but polymer amazingly could also have crystallinity, could also have crystalline structure similar like maybe metals or ceramics. However, the crystallinity will vary. Yeah, later we will see in the next slide that in metals or in ceramics, you have this crystallinity in long range order, yeah, in long range distance. In polymer, sometimes it is only available or it only exists at short distance. So this is an example of polyethylene unit cells, yeah, where the crystals must contain the polymer chains in some way. In this case, when the polyethylene chain is like this, yeah, like zigzagging, and then connected to another, and then make somehow long-range periodicity. Okay, this become its unit cell. It's therefore, as I mentioned, it is very rare that we have 100% crystalline polymers because it may have some crystallinity at one part of it, but the order it doesn't go to long distance. Yeah, and they have these regions of high crystallinity in parts of the material, while in some other part they are completely random. They are amorphous. Okay, so that is the number of material that is crystalline within that material is expressed as percentage of crystallinity. And the tensile strength and the Young's modulus often increase with higher percent of crystallinity. And this is understandable, easily understandable, because with higher percentage of crystallinity, then it means you have a long range order. And then it is more difficult to break. Yeah, that is why to bend, also to stretch. The tensile strength and Young's modulus increases. By using annealing or thermal treatment, heat treatment, it can cause the crystalline regions to grow. Therefore, the percent crystallinity will increase. So this is an example of polymer crystal form. Yeah, only if slow, careful growth is allowed will it make a single crystalline structure. Otherwise, then it will just make multiple or polycrystalline structure material. Polymer crystal form, it could make a form called a sterilite, which has a fast growth, forms lamellar or layered structure. This is, as we have seen in the previous slide, yeah, where it zigzagging like that. It is called spherulite growth. There is then a lamellar chain folded crystalline, and the region between them, this one, which has a random structure, is amorphous. Then the boundary between the spherulite is called as intersperolytic boundary. This is the polymer with spherulite as seen from polarization microscopy. Okay, so that will be all for the first hour. So let's have a break.